So this is the first video tutorial of the circle language. I thought this would be a good way to outreach and to reach more users and helping them understand and evaluate the compiler. So the conceit of circle is to rotate C++ from a runtime language to a compile time language. So anything you can do in C++ at runtime, in circle, you can prefix it with the meta token and execute the same statement at compile time. And this has a lot of amazing downstream effects because suddenly information that was always maintained by the compiler but was latent is now available for your own usage. So the type information that the compiler maintains and that it needs to maintain is now available. So in this tutorial, we're gonna develop from base principles generic object reflection for serialization of objects. All right, so to start a tutorial here, just going to create a new document, and you include standard headers, and these are parsed, lexed and parsed like they'd always be. But now we can do a printf, say hello circle, and since we've prefixed it with the meta keyword, this gets parsed and executed during source translation. So as soon as this statement is parsed, it's not inserted into the syntax tree, it's actually executed immediately. And printf not being defined in headers will involve a foreign function called to libc, which is loaded automatically by the compiler. So let's give it an empty main function just so it'll link. And we compile now. We see hello circle is printed to the terminal. Now, circle supports control flow, so let's do 5 loops through this, and let's print each loop index. And so when we run it now, oops, got to pass the index there. When we run it, we're going to get 5 iterations of this statement. Now, what's really fascinating is that this isn't a loop structure with a single child statement. The loop runs 5 times at compile time, and so it injects this statement 5 times. It translates the whole statement 5 times. So if we were to replace this not with a compile time printf, but a ordinary object declaration, we're going to expect to get 5 X object declarations created sequentially, and they're going to be initialized to 0 through 4. Now, this is fine for the first X declaration because this is declared inside the global namespace. But then subsequent declarations are redefinition errors. So when we build this, we should expect to see 4 redefinition errors. The first iteration going through and creating an object X, and then the subsequent ones creating redefinitions. So we see our 4 compiler errors right here, and it points to this line, and it's the same offending line every iteration, every subsequent iteration. So what's really fascinating is that it seems like there's an error here, but this gives us an opportunity for dynamic identifiers. So the circle intrinsic at with parentheses and either an integer or a string argument will create a identifier from the argument name. So integers are prefixed with underscore so that they're valid identifiers. So this is going to create 5 objects, underscore 0 through underscore 4, and declare these in the global namespace. So we see it compiles fine, and we can even set the objects here. So we'll say that's equals 500, and that guy is like 1,000. All right. Now, since we can execute anything, we can have side effects, and we can do I/O. And this is really important for the new paradigm I'm pushing called data-driven imperative metaprogramming. So very simply, let's create a counter and prompt the user to input an array size. So let's create an array of doubles that's count number of elements, where count is typed in by the user during translation. And then, as kind of a sanity check, let's print the type out. Type name is a circle keyword that just returns a string literal of the type name. All right, get rid of this thing. So now when we execute this, at compile time we're prompted, and we're going to say, let me 14 elements, and it echoes back that we've declared an array double of 14 elements. Of course, you'd want to develop this and generate code from files or from databases or for anything you want. Meta statements can be put in any brace scope, namespace, class definition, enum definition, or function block scope. In dependent context, the meta statement is executed during instantiation. So let's try creating a class specifier. Yeah, let's make it a template. And when this template body is instantiated, we're going to just print its template argument. Oops. Syntax error, spelling error. Okay, and we're going to let's instantiate two of these guys. All right, so the printf's only going to be executed when we translate this statement right here, because this is when this type is made complete. So we should expect to see two statements, right? And now we can extend this because this is like a very modern feature. It's fully compatible with parameter packs and all the C++ 11 through 17 features. So let's create a template that's instantiated over a pack. And the C++ way to perform an action on a parameter pack is to actually expand it into an array or a function call. The ... pack expansion syntax is only available in function arguments or the initializer list for an array or for another object. So we can create an array called x and infer its bounds, and then evaluate this printf statement. Since the printf returns an int, then this is going to be a valid initializer for this array. This is a bizarre way to do things, but this is what C++ does. So let's print out each of the types. So when this is instantiated, it'll hit this ellipsis and then expand this parameter pack, and that'll go all the way through this statement. So this should get us one printf statement per element in the parameter pack. So let's create a 3-element pack here and compile it. And we see our 3 printf expressions in this array initializer. Now this is a very clumsy way to operate. It would be better if there was a direct way to index over parameter packs. So Circle adds a new syntax, which is ... square brackets. And so if you put this after a parameter pack, any kind of parameter pack, that could be a type, a non-type, a template parameter pack, or a function parameter pack, this will yield the correct parameter pack element. So because we have compile time control flow, we can just loop over all the elements in the pack. And then we can use the direct indexing to print out one element at a time. Let's say, let's put a little note here. Type I is this type. Okay. We should expect to see the same output. Oops, statement in footy is not a member specifier. Have to put meta in there. Okay. This is just a type, and it expects a type name. There we go. There we go. So we're printing out elements of a parameter pack with imperative mechanisms. It's imperative control flow and a normal imperative printf statement. Now the natural thing is to look at this pattern and recognize we're just one step away from building a tuple class. So let's actually give this name of tuple, and we're going to try to iterate over every element in the parameter pack and instantiate a non-static data member, declare a non-static data member for each pack element. And we're going to name these elements _0 through _n-1. So the type is just the ith element in the pack, and then the name of the member is _0, _1, _2, etc. So let's create this object here. It's a tuple, and we can access them like this. So we'll set the integer member to 1. We'll set the double value to pi, and then we'll set the character pointer to hello tuple. And that actually is this is constant, so this needs to be const if we want this to work. And we can compile this. Undeclare. Oops. There we go. All right, so we've created a tuple class with just 2 lines of class specifier, and it's a perfectly flat data structure, and it's quite trivial to iterate over members, join these, to do any sort of operation you want on the structure. So we're going to now go into using introspection to generically access the data types inside, not just the tuple type, but any type at all. So let's create a generic function called printObject, and this is going to print the contents of the object, so all of its non-static data members. And right away, we're going to just assert that, use the character traits or type traits to assert that this is a class type and not a scalar type. This just gives us an argument that's kind of more pertinent to our problem than would be generated otherwise. Print object must be a class type. And we'll have to include type traits for this. Oops. Okay. So, like we did with the parameter packs, now we're going to iterate over not parameter pack members, but all the non-static data members of the class. So the member count built-in operator returns a compile time constant with the number of non-static data members in the class. And then we're going to, let's use cout because printf is not sufficiently generic here. We're going to print out the name of the ith non-static data member, and then print out its value as well. So memberref gets you an L value to the ith non-static data member when also provided an L value to the object, or a GL value to the object. So we're going to need IOStream here. All right, so we can keep this object initialized the way it had been. Let's create another object just to show that this is really doing what we're saying it's doing. And this is going to be, say, have 3 elements, doubles, and also another string. Five, 10, 15, another type. And we're going to call print object on both of these objects. All right, so this is a simple but generic serialization function. Instead of printing it just to the screen, you can print to a file. It's like the Python pickle, but it operates entirely at, the code is generated at compile time, and then it executes at runtime when it has the value of the object. So let's try building this. Let's try running it. So we see the contents of both of our structures, and if we've only written one serialization function. So we can use circles introspection to also enumerate, or to iterate over enumerators in an enumeration. So let's clear out all of this and create a function called enum to string, which will take an instance of an enumeration and return the string form of the corresponding enumerator. I find that enumerations and classes are similar in that they have iterable members, being the data member, non-static data member, and the enumerator. And so they're given very similar introspection capabilities in Circle. So this is, again, just a normal template function. We're going to do a static assert as a sanity check that yes, this is actually an enum we're given. So argument to enum to string must be enumeration. Now we're going to do a switch. So we're going to try to create a case statement for each enumerator in the enumeration. This is super easy. We can just create a meta for enum loop. So for enum statement is a Circle feature where instead of iterating over like a range-based for, which has begin and end functions, we're enumerating at compile time only. We're enumerating over all the enumerators in an enum. So we're gonna call it E2. So now this is gonna make one. It's gonna step through the for loop once for each enumeration. So let's define an enum just so if we can speak more concretely. A, B, C, D, and E. All right. So this is gonna make 5 iterations through the loop. And on each iteration, E2 is going to hold the value of A, B, C, D, or E. And E2 is also a constant. It's a meta object, which is like a mutable const expr object. Its value is known at compile time, so we can do things like specialize templates over it, or use it as the value in a case statement. So if the passed in enum E matches the enumerator in the current for step, we're going to return the string spelling, which is enum name over E2. So this is return a string literal, which is going to be put into a std string and returned. And then we don't even need the quotes here. And then finally we have a default because someone might just go in and cast some number to type T, and then we have to be able to handle this case as well. So let's put it in angle brackets. Let's call this toString. Okay, so this will return the numeric value as an integer, decimal integer between angle brackets. So if you pass it 15, it'll return bracket 15 bracket. All right, now let's try it. I can call enum to string on my enum to C, and so we're using Printf. We should get the C string pointer to it. And let's also pass it something that doesn't have a corresponding enumerator like 15. So this is the out of the range of the valid enumerators, but it should still work with our introspection function. All right. Oops. All right, so we see that we've printed out the string version of C and the string version of the 15th enumeration value. So we've just created a way to serialize enumerations and basic classes. So the next step is to join these and make a flexible generic serialization function. So let's keep enum to string because it's pretty useful, and add more functionality to what we built in the previous example. So let's go back and create yet another function called printObject. And this time we're not going to insist that it is a class type. We'll work with any type. And let's add a dependency on sstream so we can use iostreams, which is kind of useful even though it doesn't have good performance. String stream. And since this is a C++ 17 compiler, we have access to if const expr. This is only useful for function templates, but during definition, the body of both the if and the else statements have to compile. But during substitution, only the branch that's actually taken, that has only the true branch is going to be substituted. So the other branches could have code that would fail substitution, but that's okay because they're not going to be substituted at all. So this allows us to use compile time ifs. This is part of C++17, but now we're going to join it with the really amazing introspection features in Circle to get a generic introspection or generic serialization function for any kind of object. So if we have an enum type, we're using type traits here, then we're going to want to stream out. Let's just use type name. Enum to string. All right, so this will print out the name of the enumeration, : name of the enumerator. So it's a qualified name. Else if const expr. Now if this is a is same, if this is a string, or it's a const character pointer, we're going to just stream out its contents but inside quotes. So this will indicate that it's a string and not something else. So output a quote, output the data, output another quote. Okay. Another case to handle is all other scalars. So if it's not an enumeration and it's a scalar, we're gonna output it directly. If this fails for some type, which I'm not sure what type it would fail, but if let's say if you pass a pointer and it's just gonna print the pointer address, but you want it to print something else, you could definitely use a type trait and put in a special handler for pointers. All right. We're relying that IOStreams is overloaded for all the scalars here. So now let's handle array types. So isArray, and another type that's like an array is a std vector. So we're going to do isClass template. This is a circle extension. This is true if type T is a specialization of this class template. You could write a class template to help you with this, like a type traits class template, but it wouldn't be generic. So you'd actually have to write a different partial specialization for each signature that you would encounter here. So that gets like really burdensome, and I find the errors and build times are bad. So I just added this very robust generic intrinsic that works for any kinds of template parameter types here. So if this is an array or a vector, we're going to output each of the individual elements inside square brackets. So say print all array elements inside this. All right, a range base 4. And what's nice is that this works for both built-in array types and std vector. Now if we need to print a comma, we'll print the comma out. And then we'll recursively call into print object, not on the object itself, but on x, which is one of the elements inside the object. Yep. And then we're going to set comma true. So after the first item is printed, we're always going to print a comma prior to printing the next item. And then we're going to close out our list. Okay. Let's put in support for std map. Else if const expr is class template type T std map. Maybe we should add map to here. and vector. Let's print them inside curly braces. That's more like the JSON or JavaScript format. So this should be a curly brace. Should be a curly brace. Now what's different about, we can loop over using range base 4, but now x is not a single, it's not a single element, it's going to be a pair, it's going to be a key value pair. So we're going to want to print the key and the value separately. So let's call print object on x.first, and this will print the key, and then let's print a separator, a colon separator, and then let's print the value. Okay. And that's all we have to do there. Now, we could add all the STL types. We could do like a stack. Well, you can't really like look inside a stack. Let's find like on list, set. You know, you could fill that out however you want. We're just gonna close this up now and do the last remaining type, which is any other class type. So since we've already handled scalars, the only thing left are class types. So let's just do a sanity check that we do have a class type. Expected class type. Now print all. This would be map elements. Print all non-static data members inside curly braces. This is the same pattern as what we've done before. So print out a curly brace. Create a separator. Now we're going to loop over all the non-static data members, which is member count of type T. Okay. If comma, print out a separator. Now we're going to print a key value pair where the key is the name of the non-static data member. And then we're going to print out, we're going to use print object to recurse and print out the value. So we're going to print object of member ref of object. And then we're going to close up the braces. All right, and now we just have to return oss.str. And this is a recursive, extensible, generic serialization class, which prints out a JSON-like string version of any type. There could be things like access violations, or access protection violations. There could be other reasons this fails. If that happens, then you would add the necessary adjustments here as different cases to suit all the types that you're going to specialize print object over. All right, so let's create some types here. Let's go back and whip up another tuple because it's so easy. T. Size of dot 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 is part of C++ 11, but there wasn't really much use for it in C++ 11 because you couldn't iterate over pack elements and you couldn't index into the parameter pack. But it's very useful in Circle. Okay. And here, let's create a tuple, a big one. Int. So this is a scalar type. This is an array. This is another scalar type. No, this is not a scalar type according to our serialization function. This will match the string pattern because it is a const character. So it'll be quoted. And finally, a map where the key is a string and the value is an int. And then we can use the braced initializer, which is a feature in C++ 11 that's pretty convenient. I use it a lot. So I'm initializing the 3-element double array right here. Now I'm going to initialize the character pointer and have it point to the hello tuple string literal. And then finally, I'll use an std initializer list constructor for std map and give it 2 elements, hello, and give this a value of 100, and world, and give this a value of 200. So this is an automatically generated, implicitly generated constructor that will initialize all 4 members of the aggregate. And we're going to print this to the screen. Certainly there's going to be some compiler errors because I never get anything right the first time. All right, let's fix some errors now. Oh, it compiled. Does it work? And it works. So let's make this a little bit bigger. So we see the 4 non-static data members printed out here with their names. So this is a class type. So it's going to go through and it's going to hit initially the generic class handler, which is going to print out braces, loop over at compile time, loop over all 4 elements, and then inject this code for each of the 4 elements. So it'll start off by printing the member name for element 0, and that's _0. It'll then recursively call print object on the 0th non-static data member, which in our case is just int1. So that'll recurse back up here. It's not an enum, it's not a string, it is a scalar, so it'll use this overload of the ostring stream object, and we have a 1 there. And then we go through a second time back here, so I = 1 is member name _1, which is a L value reference to double 3, a 3-element double array. So that'll be matching the array type trait. So it enters here, and then we're going to get a square bracket list of comma separated elements. So we have a square bracket list of comma separated elements, and this is going to return, and then we're going to be on I equal 2, which is name _2, and that is a const character pointer. And so when that recurses, it'll match this case. So it'll print the contents of that string inside quotes. So it looks like a string, and in a JSON or really any other language, this would be interpreted as a string as opposed to a value or an identifier or anything else. And finally, we're got I = 3, which is a std map with a key of string and a value of int. So that will match this case, because isClassTemplate, yes, type T is an instance of std map. So we're going to print out curly braces, and then we're going to use a range base 4 over that whole red-black tree, which is the internal data structure for std map. I'm going to visit all the elements. The type inference here will make this a std pair, where x.first is the key, and we're going to recurse on the key, and the key is a std string. So it's going to hit this block again, but now because it matches std string, prior to it matched the const char case, we're going to print out the contents of that string inside quotation marks. That's the key right here, and that's that key. And then we're going to do this same thing for the value. The value, which is just an integer, so that's going to hit the scalar case. And we see the integer. So we've got a full, like a JSON-like serialization that works for just about any class type, and it's really flexible. So if we want to add things like std optional support, we can add that here as well. So I'm going to put another tutorial together later on domain-specific languages and how circle macros can help you lower IR to code. This is a very simple tutorial here on the tactical aspects of circle, and the next one's going to be on the strategic aspects of circle. Thank you.